Swastyastu, Assalamualaikum warahmatullahi wabarakatuh. Syallom, Namo Budaya, Salam kebajikan. In this video, I will explain about heat treatment of non-ferrous alloys. First, let me introduce myself. My name is Elkana with name 230553173 from Metalurgi class C. This lecturer, Prof. Dr. Tjokorda Gde Tirta Nindhia, MT Engineering. Book reference: Metalurgi for this Non-Metalurgist, Seccond Edition, edited by Arthur Riardon. Contents: Point 1, recovery and recrystallization annealing. Point 2, heat treatable aluminum alloys. Point 3, cobalt alloys. Point 4, copper alloys. Point 5, magnesium alloys. Point 6, nickel alloys. Point 7, titanium alloys. Point 8, other non-ferrous alloys. Heat treatment of non-ferrous alloys. Non-ferrous alloys are heat treated to tailor their properties for a variety of purposes include 1. Aiding in recovery by reducing internal stress. 2. Promoting diffusion by redistributing exciting alloying elements. 3. Promoting new equalized grain formation. 4. Promoting grain work. 5. Dissolving paste. 6. Producing new paste by derivation from solid solution. 7. Altering surface chemistry by the introduction of foreign atoms. 8. Promoting new paste formation through the introduction of ferric atoms. Recovery and recrystallization annealing. Annealing is a generic term used to denote a thermal treatment process that consists of heating a material to ambient temperature and holding or soaking it for a sufficient length of time that temperature, or by cooling at a stable rate. When annealing is performed for the periods of time or at low temperatures, the harps of a cold work alloy remains relative constant. This initial stage is referred to as recovery annealing in the picture below. Okay. Although the level of thermal activation is not sufficient to significantly affect hardness during recovery, there is some movement requirements of dissolution during the recovery stage. Thus, some properties do change during recovery annealing. For example, the electrical resistivity of an alloy is typically increased by cold working, but can be recovered before annealing has a significant effect on hardness in the picture below. The onset and extent of recrystallization depends on many factors, such as compression, grain size, and extent of cold work. For example, an increased amount of cold work prior to annealing lowers the recrystallization temperature in the picture below. There also is an approximate relationship between melting temperature and recrystallization temperature in the picture below. Following recrystallization, the energy of the alloy is reduced further by a decrease in the grain boundary or by grain growth. The microstructural change the core during annealing are illustrated in the picture below. During recovery, there is decrease in the descent of the formation bonds, although this effect is not permanent. Heat treatable aluminum alloys. Rock and cast aluminum alloys are commonly designed by cells original by alpha. Heat treatable aluminum alloys include 1. Pure aluminum 1000 rock and 100.0 K series. 2. Aluminum magnesium alloys 3000 rock series. 3. Aluminum silicon binary alloys 4000 rock series. 4. Aluminum magnesium binary alloys 5000 rock and 500.0 K series. 6. Other miscellaneous alloys 8000 rock series and the 800 and 900 K series. Rock heat treatable aluminum alloys include the aluminum copper 2XXX series, the aluminum magnesium silicon series 6XXX, the aluminum zinc 7xxx series and the aluminum lithium alloys of the XXX series. These alloys achieve higher level of static tensile strength but with less of improvement in the fatigue endurance. In the future goal, considerable aluminums include the aluminum copper 2xxx, some the aluminum silicon plus copper and magnesium alloys 3xxx, and the aluminum zinc alloy 7xxx. By far, the most widely used of the aluminum casting alloys are the aluminum silicon alloys with magnesium and or copper. Cobalt alloys. Cobalt is useful in application the makeup of its magnet properties, corrosion resistance, wear resistance, and strength at elevated temperatures. Bimetal application is another important use. The initial bimetal field application of cable-based alloys were in the dental field, and early evolution of this alloy shows excellent wear resistance, corrosion resistance, biocompatibility, and mechanical properties when used in people as orthopedic implants. Copper alloys. Copper can be hardened by solid solution alloying and by hardening. The commonly used solid solution alloying elements lesson in approximates order of increasing effectiveness are zinc, nickel, magnesium, aluminum, tin, and silicon. The treating process that they apply to copper and copper alloys include homogenizing, annealing, sterilizing, solution treating, precipitation or hardening, and quench hardening and tempering. Precipitation hardening copper alloys. Edge hardening mechanisms are used in a few but important copper systems that include 1. Edge hardening beryllium copper alloys, 2. Edge hardening chromium copper alloys, 3. Edge hardening CuNiSi alloys. Edge hardening copper alloys can be thermochemically pressed to provide an equal combination of strength, formability, electrical conductivity, softening resistance, and stress relaxation resistance. As an example, the solution treatment of beryllium copper alloys is performed by heating the alloy to a temperature slightly below the solid in the picture below. To dissolve a maximum amount of beryllium, the repellent quench to the material to room temperature to the beryllium is an superstarred solid solution. Spinodal hardening. Copper alloys are basically copper nickel alloys with chromium and or tin addition. Composition in the CuNiSi system are C71900 and C72700 alloys. Spinodal hardening involves different types of transformation that of precipitation hardening because it does not involve nucleation steps. Precipitation hardening involves the classic process of nucleation and growth, where flat fluctuations in composition must reach thresholds for further growth. Flexion below the critical levels for nuclear formation do not grow. The picture below. In contrast, spinodal reaction involve continuous or homogeneous clustering or mixing of atoms in top heads by spontaneous growth from small composition fluctuation in the picture below. The chemical disintegration occurs on a very small or extreme levels scale and requires the use of the electron microscopes to be described in the picture below. The microstructure develops during spinodal decomposition has a characteristic periodicity is typically 2.5 to 10 nanometer in metallic systems. Ordering hardening copper alloys hardening refers to surface hardening of solid atoms within metallics. In generic occurs from low temperatures and the hardening of solid greatly impairs discoloration motion. With treatment of aluminum bronze include two types. 1. Single pass aluminum bronze alloys with a VCC or a phase crystal structure. 2. Two-phase aluminum bronze alloys that consists of an FCC or a phase with either a body center cubic BCC, B solid solution phase high temperature, or an AL4CU9 precipitate H2 at lower temperature in the picture below. C0 like activity still Fa 0.77 C if an alloy composition of Cu 11.8 AI is low called from the way to be best, then the microstructure forms distinctive lamellar structure in the picture below, much like prevalent is in steel. The martensite starts or in its temperature is approximately 380 Celsius Cu 11.88 AI. The microstructure of the biaxial has the distinctive knit-like or plate-like morphology of martensites. In the picture below, the treatment of bias composing alloys comprise four steps of press that have along a bit of great commercial importance. Copper with zinc solid solution alloys are probably the most widely used copper-based alloys. Zinc has an HCP crystal structure, so the solubility in copper can't be complete. However, FCC copper is also packed with an atomic size difference of only about 4%, which things thus solubility is extensive. In the picture below, copper zinc alloys can give martensite sparks during coatings. An important example is martensite in CuZlAI. Self-memory alloys in the picture below. Other heterable copper alloys among the other binary alloys that can be aged hard the copper titanium, copper magnesium, copper silicon, copper silver, copper iron, copper cobalt, and copper zirconium alloys. Magnesium alloys determine and improve the mechanical properties of magnesium casting alloys. In most work alloys, maximum mechanical properties are developed through standard, and these alloys generally are either used without subsequent treatment or merely aged to a T5 temper. Occasionally, however, solution treatment or a combination of solution treatment with standard and activical zincs will substantially improve mechanical properties. Preparation occurs in many magnesium alloys, but preparation doesn't always result in hardening. Some examples of significant hardening that does occur for precipitation include magnesium aluminum alloys in the picture below, magnesium lithium alloys in the picture below, and magnesium zinc alloys in the picture below. Nickel alloys. Nickel is obtained from an allotropic phase transformation occurs in a nickel or the high nickel family of alloys. The alloys are obtained from the melting temperature down to absolute zero. As hardening of nickel-based alloys, the addition of niobium or aluminum, silicon, titanium, and certain other alloying elements to nickel and nickel alloys separately or in combination produce an applicable response to age hardening. The effect is dependent on both chemical composition and age temperature. It is caused by the precipitation of submicroscopic particles through the grains, which result in a marked increase in herbs and stings. Some example of age condition for some superalloys are shown in table 14.9. In terms of microstructure, the Z-action precipitates has a rather unequivocal morphology. The size is determined by its condition and illustrated in the microstructure of an individual below. Titanium alloys. Titanium and titanium alloys are heat treated in order to reduce residual stress developed during fabrication or string labor to produce an optimum combination of ductility, malleability, and dimensional and structural stability or annealing. 3. Increase strength or solution treating an edge for optimized special properties such as fracture, toughness, fatigue, stir, and high temperature clamp strength. Always elements either rise or lower the temperature for the A to B transformation of transformation, so allowing elements and titanium or plastics is either stabilizer or stabilizer. The stabilizer dissolves preferentially in the phase, expand the files, and rise the alpha or beta transus. The picture below. Beta stabilizer reduces the alpha or beta transus and stabilizes the beta phase. There are two types of B stabilizers. One is supposed B stabilizer, the from binary system in picture below. Beta stabilizer, the conformation of beta ectatic in the picture below. Microstructural fracture of titanium alloys. Generally, two types of alloys may be present in titanium alloys after treatment. One primary, which versus stock treatment, and the treatment from pure outworking of or processing. Two, secondary, also referred as the transfer B, which is produced by transformation of B during or after treatment. Primarily, might be adopted or excited depending on bioprocessing and treatment. For example, three different morphologies of L, primary and alloyed titanium, are seen in the microscopes in the picture below. The amount of B pass and transfer B secondary A becomes more predominant in alloys such as Ti6IL, 2S8, 4GR, 6MO in the picture below. Depending on the cooling, the areas of secondary paths have different occurrence or shapes that are described as lemur, plate-like, equilateral, with mistakes sorted of mathematics. For example, in the picture below. So, microstructure of an alloy that's well loaded and 12 and 77 Celsius and coke are the different grades. Beta stabilizers or the NA temperature are listed in the picture below for the variations of vanadium content at to a Ti6AI composition. The MS temperature is also a function of handling temperature for B alloys, as illustrated in the picture below for Ti6AI for fifth F. The typical temperatures for matrix formation by quenching are shown in the picture below. For some titanium alloys, sometimes it is difficult to distinguish between alpha oxide, martensites, and occur a laptop and occur actually is less well defined and has soft rather than straight lines. A summary of its times and temperature is present in table 14.4.12. Zinc is now carried out in the range of 425 to 650 Celsius in the picture below. So come general factors of the aging process. As the aging process process in strength increase to maximum, the gradually decrease. Of course, there is intended trade of between strength and ductility. Titanium alpha alloys, unlike the alpha, beta, and the B alloys, the alpha and the alpha titanium alloys can be strengthened by heat treatment. The is listed by in the picture below. Of these four treatments, the strength is not improved, but there is a sharp drop in the ductility of four heat treatments above 10 Celsius. This drop in ductility is attributed to the formation of more alpha from the transformation of B developed in the higher temperatures. However, resistance to creep deformation is improved by the formation of equilibrium alpha. The heat treatment of 10 and 65 Celsius is above the B-transas, and rapid cooling results in a microstructure that has a calcular alpha and martensites. Although this structure is not ductile, it does provide more creep resistance in the picture below. Titanium alpha or beta alloys are the most common and the most versatile of the three types of titanium alloys. If high fracture toughness or improved resistance to stress corrosion is required, then annealing or solution treating may be desirable. The alloys are usually solution hydrated below the B transfers to option an optimum balance of ductility, fracture toughness, grade, and stress fracture properties. If the beam transfers is accurate, the tensile properties of alpha with alloys Especially the activity are reduced in the picture below and can be fully restored by subsequent treatment. Titanium beta alloys, the principal final treatment for beta and near wheels concept of aging of material previously be annulled and better concept. The non-ferrous alloys, iterable silver alloys, the precious metals including silver, behave somewhat similar to copper and nickel. The most important silver alloys are the silver copper types. Copper is added to increase the hardness and strength of silver, with this effect of the electrical conductivity is small compared to the of the other additions. Iterable gold alloys, the gold alloys which find application in the jewelry or setting. They are an industry generally contain silver and copper, and sometimes zinc, nickel, platinum, and palladiums. The properties of an considerable number of these alloys are altered by different testings. Achievable low melting alloys, or ZMPBCM. Zinc-based alloys can then improve subtly by treatment of where the commercial consideration of such alloy practice. However, they exhibit some essential irregularities and properties caused by proportion and transformation properties, processes which are of considerable importance in die castings, but the zinc copper and zinc aluminum alloy system process things that affect the properties of die castings. Uh, that's all the material I can tell you. Thank you. Om Santi Santi Om. Waalaikumsalam warahmatullahi wabarakatuh. Shalom Namo Budaya. Salam.